The second gas law I'm going to talk about is named after Charles. This is called Charles's law, which relates volume and temperature. Now, Charles's law says the volume of a fixed mass of gas at a constant pressure. Remember, like the three things that we're looking at: volume, temperature, and pressure. If we're comparing volume and temperature, then pressure stays constant. The volume varies directly with the Kelvin temperature. So this is a picture of Charles. And again, like I've explained in the last video, a direct proportion, you end up with a line like this. So what I want to do is show you how that equation is derived first. So he says volume is directly proportional to temperature, which means if we want to make an inequality, then we have to introduce the constant of K. So we can say volume is equal to K times T. And so that we have a constant on one side and all the variables on the other, we can rearrange that to equal V over T equals K. And now we can compare initial and final volumes and temperatures by introducing 1 and 2. So if V1 over T1 equals K and V2 over T2 equals K, therefore, that's what the symbol means, therefore, V1 over T1 equals V2 over T2. And this is the formula for Charles's law. Now, one of the important aspects of the gas laws, especially when considering temperature, is that all of the temperatures are measured in a unit called Kelvin. It's the Kelvin scale. Sorry, I wrote all over that. So in order to convert Celsius into Kelvin, you just add 273 to the degrees of Kelvin. All temperatures in the gas law problems must be in Kelvin. So you have to make sure that you convert all of the Celsius to Kelvin first. Let's practice. A sample of neon gas occupies a volume of 752 ml at 25 degrees C. What volume will the gas occupy at 50 degrees C if the pressure remains constant? So we're given V1, which is 752. We're given T1, which is 25. I'm going to convert that to K immediately. So 25 plus 273 is 298. And we're given T2, which is 50 degrees C plus 273 is 323. And our unknown is V2. Okay, so just stipulating our given and our unknown. We're going to use the equation V1 over T1 equals V2 over T2. And solving for V2, which is our unknown, we get V2 equals V1T2 over T1. We're just going to take T2 and multiply that on both sides. So then the only thing we have left to do is to plug in our numbers, and we cancel our unit of Kelvin, and we get 815 ml of neon. So let's do some practice. A helium-filled balloon has a volume of 2.75 liters at 20 degrees C. So I'm just gonna go ahead and write down the information we're given as we're given it. V1 is equal to 2.75 liters, and T1 is equal to 20 degrees C plus 273 equals 293 K. The volume of the balloon decreased to 2.46 liters after it was placed outside. So my V2 is equal to 2.46 liters, which means I'm solving for T2. What is the outside temperature in Kelvin and in Celsius? So they were going to have two answers here. So the first thing I'm going to do is write out my equation, V1 over T1 equals V2 over T2. I need T2, so I'm going to solve for T2 by moving T2 up here and then multiplying this side by T1 goes up and V1 goes down. That's how I do it, like just cross multiply. So I end up with T2 equals V2 T1 over V1. okay, which is all the things I have here. So I'm just gonna substitute the numbers in there. So V2 is 2.46 liters, T1 is 293 K, and V1 is 2.75 liters. I cut liters. I need to bring my calculator out, which is here. I gotta go back here, and then I gotta go whoop, and whoop. I'm gonna put it on this side. So I've got 2.46 times 293 divided by 2.75, and I get 262K. Now that's K. What is it in C? If you want to go from K to C, you subtract 273. So I'm minus 273, and that equals negative 10.9 degrees C. And Bob's your uncle. That's it. Okay, pretty straightforward. Okay, 10.9 or 11, same thing. Next, I'm gonna put it, is it maybe covered out? So I got V1 over T1 equals V2 over T2. A gas at 65 degrees C, so that's T1. 65 plus 273 is 8, and that's 13, 338. Occupies 4.2 liters, so that's 4.22 liters is V1. At what Celsius temperature will the volume be? That should be at 3.87 liters, assuming the same pressure. So volume 2, 3.87 liters. So again, we're solving for T2. So rearranging this equation to solve for T2, I've got T2 equals V2 T1 over V1. And substituting my numbers, 3.87 liters times 338 over 4.22. Cutting liters, bring back my calculator. Come on, come on. There we go. And let's see, 3.87 times 338 divided by 4.22 equals 30, let's make that 310. And that's 310 Kelvin, because I forgot my K. Bad teacher, forgetting her units. And I forgot to mention with the last practice problem, didn't think it was that difficult to say. The last practice problem, is to double check your answer to see if it makes sense, because if you understand that they have a direct proportional relationship. So if in this example, we go from 4.22 to 3.87, I didn't even finish the question, did I? We go from 4.22 liters to 3.87. That's a decrease in volume. And if volume and temperature have a direct proportion, that means that temperature should also go down. So let me go ahead and finish this, this question by actually answering it, because it does say what's the Celsius temperature. So move. I want to move. Okay, fine. All right. Okay. Oh, okay. I can do half. I guess maybe you guys can't see that because I'm only sharing my Keynote screen. So I guess you can't see my calculator. Ew. Well, you know what? It doesn't matter because you got your own calculators, right? So I'm just going to do 310 minus 273, and I get 37 degrees C, since that is what the question asked for, the Celsius temperature. So it makes sense because our volume has decreased 4.22 to 3.87, and our temperature has also decreased 65 to 37. So yes, it makes sense.